All right, thank you. So this is joint work with John Schneider and Matt Weinberg at Princeton. And as Bobby mentioned, there's ample examples of why incentives and competitions matter. He mentioned the 1982 World Cup, which was uninvestigated. A more recent example that is very well known in the AGT community is the women's badminton doubles in the 2012 Olympics, where I'll just sum it up quickly. But basically, a very good team had an unexpected loss in the group stage, and then other teams learned this result and try to purposely lose their matches in order to avoid this very good team on the upcoming second phase of the group, which was a single elimination bracket. Okay, and you can imagine this was unilateral teams, teams unilaterally being untruthful in order to improve their chances of winning the tournament. You can imagine reasons why teams might collude in order to increase their chances of winning, and this is sort of what we try to investigate in this paper. So what is a tournament? How do we model tournaments? So we will have directed graphs on end players, complete. So there's an edge from team I to team J if team I beats team J. So here you have an example. Team A beats team B here. Tn is a set of tournaments on end players, and we're considering we have a complete graph on end players that's directed and has all the edges. So we want to find a rule that, given a graph, chooses a winner somehow, and we allow this choice to be randomized. So RIT is just the probability that team I wins a particular tournament. And we say a rule is Condorcet-Consistent if whenever a team wins all their group stage matches, or when they beat every other team, then they're declared the winner with probability 1. And we think that this is a very reasonable and important property when considering competitions like the World Cup or the Olympics. It seems very fundamental. So here's a small example. So we have Arsenal beats Chelsea, and they also lose to both Manchester teams. Chelsea beats both Manchester teams, but loses to Arsenal. And then, of course, CD beats United. So here's a tournament. How can we choose who wins this? Many rules are can be thought of. You can say, okay, what about the team with the most wins? There's more than one. Can we flip a coin? Can we make a bracket? But then choosing the right bracket will definitely favor some teams over others. However, it would be very obvious who should win if Chelsea beat Arsenal instead, because then Chelsea would win all their games and they would be the Condorcet winner. We could all agree that they should win the tournament. So this is sort of what our model of a tournament is. So how can teams manipulate tournaments? That's the real point of the question. So we choose a subset of teams and we say two tournaments, so two directed graphs, are S adjacent if they agree on all the edges that don't have both endpoints on the set S. Or in other words, we allow the teams on this subset S to arrange the results of the matches whichever way they want. Okay? And we say a particular rule, a particular way of choosing a winner is 2 strongly non-manipulable, or 2 S&M, if for any 2 players in any 2 tournaments that are adjacent by that edge, the probability of their joint probability of winning is invariant. So meaning that they don't benefit jointly from the collusion. Okay? And this is just expressed in this condition. The probability that I and J win on tournament T is the same as if it's the same if J beats I as if I beats J. That'd be the way to think about it. Unfortunately, as Bobby also mentioned and proved with Altman, this is impossible. We cannot have tournament rules that are both 2 S&M, meaning that teams don't have incentives to collude, and also Condorcet-Consistent, meaning that we give the prize to a team that beats every other team with probability 1. Okay? And just to settle down this notion again, here's our example from last time. So this tournament is now Arsenal-Chelsea adjacent to the one I showed on the previous slide. I flipped this little edge. So now Chelsea is a Condorcet winner. They win all their matches, and they would win this tournament with probability 1 if our rule was Condorcet-Consistent. Okay, so bounding manipulation. So as I said, we can't get both Condorcet consistency and 2 S&M, and we really don't want to compromise on Condorcet consistency. You couldn't imagine the World Cup or the Olympics having someone beat everyone else and then not getting the gold medal. So our work addresses the question of relaxing the 2 S&M condition in a sort of worst case manner. So we say a rule is 2 S&M alpha if the gain in probability that the teams get from colluding is bounded by some alpha. Okay, for every pair of teams and for every pair of adjacent tournaments for these 2 teams. while preserving Condorcet consistency. And morally, what we're trying to do is we're trying to say, okay, let's bound how much any two teams can gain on any tournament from acting untruthfully together, from cooperating. And the main result of this paper is very surprising. Single elimination brackets with randomized seedings are optimal for this metric. And in particular, you can't get around this factor of a third for alpha. And no other Condorcet-consistent rule can do better than this. Okay, so I will show in the next couple of slides an example of a tournament. So an example of a particular set of outcomes for matches, such that no Condorcet-consistent rule can prevent an incentive of 1/3 for teams to collude. And on the other side, we will show that single elimination bracket with random seeds does no worse than a third. Okay? And other common rules do poorly in practice, in the worst case, sorry. So a very popular rule, the one that they use for most soccer leagues or sports leagues in general, is called the Copeland rule. The team with the most wins in general, but points is what they use, wins the tournament. That does pretty poorly under this metric. There we go. But I will not go into the details of that. There's a lot of related work. Tournament design is, been very active even before the Olympics scandal. There's all this work in the tournament fixing problem, along other things in voting theory as well. I will not have time to go over these, but it's very good work. So the lower bound, very simple example. So we have three teams that are really good: Charmander, Squirtle, and Bulbasaur. Charmander, Squirtle, and Bulbasaur. They beat each other cyclically, as you would expect. And then we have N-3 Jigglypuff teams that lose to everyone, to these three teams, and we don't care how they do against each other. And the point is that any two of these teams can form a Condorcet winner by just flipping that arrow. So if say Squirtle threw to Charmander, then Charmander would be the Condorcet winner. They would take the tournament with probability 1. So then we get equations of this kind, bounding alpha, add them all up, and we get a lower bound of third for alpha. Another way to think about this is, that we have three teams that are very good here. Any two of them cannot have a probability of winning the tournament greater than 2/3 combined, meaning that there are two teams that have at least 1/3 incentive of throwing their respective game. Okay, and this is, again, irrespective of whichever rule you pick. There's always this example, and it's pretty pathological, but it's a worst case analysis, so there it is. The upper bound is pretty impressive or surprising. Random single elimination is tight. I'll only show this in one slide. I'll give you a taste of the proof very briefly, but it's not complicated. It's very cute. But basically, this is what we call a bad bracket. So we have teams I and J that are trying to collude, and truthfully, J beats I. But in this particular bracket, in this particular random seed of the teams, Team J beats Team I, but Team J doesn't have they don't end up winning the tournament. So maybe Team I could benefit from Team J throwing this respective match, and then maybe they have a chance of winning. Maybe J is the last team that beats Team I, and they're friends, so Team J will lose to Team I. And Team K here is just some other team that beats Team J that will be relevant for our construction. But again, bad brackets. I and J play against each other. J truthfully beats I but has no chance of winning the tournament. So there is some incentive for I and J to collude. And we basically take bad brackets and we transform them into good brackets. And we show that there are twice as many more good brackets than bad brackets. So in this case, we construct a good bracket by just getting this subtree of K that beats J and moving it to where the subtree for I is. And now I and J don't meet. And in fact, J gets eliminated before he could possibly meet Team I. So there is no more incentive for these two teams to collude or cheat or act untruthfully. And again, this is like a very quick taste of the proof. So let me just slow down a bit. I think I went a bit too fast, but let me slow down and go over the moral takeaways of the talk. So, as many results in AGT, we don't mean to be particularly prescriptive, but sort of like we tend to, give guidelines on how to run things. And one of the recommendations that we think is good is, for instance, instead of so what happened in the 1982 World Cup, basically teams played with the knowledge of the final outcomes of other teams, meaning that they could perfectly plan how to, guarantee that they would both advance. So a way to prevent this is to have matches played simultaneously, which is actually what came out of that scandal. If you notice now, the last game of the group stage of any World Cup is played simultaneously to avoid this sort of like collusion. Also, all of our results also hold for the case where, instead of having 0-1 or instead of having like directed edges, you have probabilities. Team I beats Team J with a certain probability, which makes the model sort of more realistic. It turns out that the 0-1 case is actually the hardest. Also, we can define, this is interesting, further work, maybe open problems to think about. We can define the same problem for larger collusions, which we call KSNM alpha rules. It's the same definition, except that now we allow for up to K teams to try to gain alpha mass from arranging the matches in whichever way they want. And a very simple example, similar to the one that I gave before, gives a lower bound of k-1 over 2k-1. But we don't know if this is tight. We cannot think of any simple tournament rule or even any tournament rule that achieves this. And we conjecture that this is the right bound, but we're not sure. And a good thing to think about maybe is, can we find a rule that is KSNM a half for every case, since this tends to a half? That seems like a plausible, nice thing. Or maybe just try to understand what happens when we have collisions of size 3. And the last thing that is sort of inspired by some of the related work, as I said, the example that exhibits the lower bound is pretty pathological. Maybe you can say, okay, real tournaments don't look like that. There aren't really 3 teams that beat everyone else. They tend to be more even. Maybe there's like layers or sort of like tiers of teams. So the rules that we use, like the Copeland rule, the rule that you chooses the team that wins the most matches or has the most points, are those like still pretty non-manipulable under like more common graphs. All right. So that's that, and thank you. If you have any questions. Yes.
So first of all, a knockout tournament, I think it has all the perfect properties. Am I right?
Yeah.
So if you can control the way the tournament is done and not let every team play against every team, then it's also a direction how you can, in some sense, improve, right?
So the way we think about this is, first you have the round robin where everyone plays everyone, and then you need to find a rule to pick a winner, right? Yeah. So the bracket itself might not actually be played. Right.
No, but in a more practical.
Oh yeah, sorry.
In a more practical, just don't let every team play against everyone, and then maybe and then essentially there are. If you also design who will play against who, then it somehow can create much better tournaments. No.
Yeah. So some of the work that is related actually examines a similar question, which is what happens when the designer of the tournament and one team collude in order to try to help that team win. This is the tournament fixing problem, and there's interesting results there. Yeah. Sorry.
I think we better.
Yeah. Hurry up.
Let's thank Ariel once more.